Yeah, welcome everybody to TACC. It's my great pleasure to give you this introduction to TACC here today. Dan is unfortunately busy with securing some funding for the center. You may know that most of our funding is coming from, soft sources, so there's always a lot of activity about regarding funding. Yeah, my name is Lars. I started at TACC in 2007. And that is basically when we built Ranger, which made, the top 10 in 2008. And that was a big splash, and that put TACC on the map. TACC is a big x86 shop, and CPU performance is very, very important to our broad user base. Of course, many users are now moving on to GPUs, and many of the most popular or most widely used codes have been ported to GPUs, but many smaller codes have not. And also many pieces of complex workflows have not been ported to GPUs. So x86 or CPU performance is very important for us. And I have highlighted here the systems, the large production systems that we have had since Ranger. So we had Ranger that started in 2008, and after that, that was replaced by Stampede 1 and then Stampede 2. And while those were the big NSF production systems, we also have kind of the Lone Star series, which is for local users, Texas users, UT users, Lone Star 4, 5, and 6. And then some years ago, we started Frontera, and I will talk about that architecture in a little bit. CPU performance is important, and also the successor to Frontera, the system that we are building currently, named Horizon, will have a large CPU partition, while other centers may have basically all the performance in the GPU part. We will not follow that path. I saw there was something in the chat. Oh no, that was not a question. I just tried to look at the chat. And please interrupt me if you have a question or a comment. Yeah, so we are currently operating 3 big production systems for the NSF, or mainly for the NSF. That is Frontera, Stampede 3, and Vista. And then we have Lone Star 6, which is traditionally all the systems that are called Lone Star are for UT Austin, UT Systems users, and also for our industry users. Here I have a little summary of how many servers that the total is. So it's quite an ensemble of nodes, over 1 million of cores, and we hand out to our users billions of core hours over per year. I mean, internally we use more the node hours. Yeah, TACC is a big outfit. The number here is a little bit old, so it's 190 staff, 70 PhD. I think by now we have grown to 230 in staff. Here's a picture on the right. That is Lone Star 6. It's cooled in oil, so it's immersed in oil. Most of the Lone Star 6 nodes, and it comes in this big tomb-like contraption that holds all the nodes and all the oil. Everything that we do is basically for unclassified and open science, and that means that our services are free for users, any user at a U.S. institution, or also worldwide if you have a collaborator in the U.S. So the only requirement is that you are at a U.S. institution, or that you're collaborating with somebody at the U.S. institution, and that you do unclassified work that will be published in scientific journals, and that you do open science. So here are 2 examples that come out of the field of astronomy, but of course we cover, our in quotes, customers do, of course, science in all fields of research. I'd like to walk you a little bit through the three main systems that we have. Here's, first of all, is Frontera. That's our largest system, over 8,000 Cascade Lake nodes. So there are these are all dual core, dual socket nodes. They have 192 gigabytes of RAM, and if you multiply that with 8,400 nodes, you can see that we can host quite large applications with large memory footprint. And then everything is, all these clusters have a connection with high-speed InfiniBand or something similar. Then there's a file system and all that kind of stuff that you need to run a large system. Frontera is getting old. There's really no way to say it otherwise. It's in the 6th year of production now, but it is still going strong. So uptime is still very, very high. We have a lot of high average utilization, millions jobs completed probably over a year. The performance of a single node is still kind of okay. As I will show you in some upcoming slides, I will compare performance with other x86 architectures that are newer. So single node performance is still okay. But with 8,000 plus nodes available, there's of course a large aggregate memory footprint that we can host. So we all of our large customers that we have, they run on Frontera. But the bread and butter of even a large system is the fact that many of these jobs are small jobs. So here some statistics that Dan always likes to highlight. There were 2,000 plus nodes, where more than 512 nodes were used. But the majority of nodes of jobs are of course short, and there are single node or dual node, something like that. So small jobs represent 30% of all jobs, but only 2% of the cycles delivered. But it is very, very important for us to provide a platform that can handle these many small jobs, because many workflows are based on that. There are large jobs where most of the SUs are consumed, and then in the pipeline, in the workflow, there has to be also many small jobs. And we of course adjust scheduling priorities to have a high utilization on average for the system, so that we can serve our community the best. Here's a picture of Lone Star again. This is for research computing at the University of Texas and other contributing partners. Texas A&M, for example, is a partner, Texas Tech. It's a much smaller system, 560 nodes. Most of these nodes are immersed in oil. We have some nodes that are not shown in the picture. Lone Star has grown out of this coffin-like contraption, and so there are some air-cooled nodes as well. And Lone Star has a quite large GPU partition as well with 240 A100 GPUs. I want to highlight a little bit and talk a little bit about Stampede 3, because that is the system that is now hosting 3 different CPU architectures, as well as some Ponte Vecchio nodes. So when we transitioned from Stampede 2 to Stampede 3, we did that because the file system was falling apart, and so we needed a replacement for the file system. But the nodes itself were still highly resilient, and they were performing very well. So we moved quite a lot of nodes from Stampede 2 to Stampede 3. So you can see here the nodes here in the upper part of the slide. You can see over 1,000 Skylake nodes, and all of the Ice Lake nodes that we had in Stampede 2 were moved over to Stampede 3, and then we added 560 Sapphire Rapids nodes with HBM and 20 Ponte Vecchio nodes. And then there's a new network and, of course, a new file system. This time we moved away from Lustre, where we have a 10 petabyte vast file system and an omnipath network. Now, with these different technologies in Stampede 3 and also with the Cascade Lake nodes in Frontera, we can readily compare performance of Cascade Lake, Skylake, Ice Lake, and Sapphire Rapids. And that is what I'm going to walk through now on my next slide. So here we are comparing Cascade Lake nodes. All the performance is normalized to 1 on Cascade Lake. And you can see how on a single node, a Sapphire Rapids node would perform with DDR5 and the Sapphire Rapids node with HBM. So in Stampede 3, let me go back to the previous slide, we have 565 Sapphire Rapid nodes with the HBM. Those are the production nodes. But for some, for testing, we also have some Sapphire Rapids nodes with DDR5. And you can see, on average, I would say Sapphire Rapids is about 2x more performant than the Cascade Lake node. And for some applications, the high memory bandwidth that is provided by HBM memory is particularly very important. So, for example, PSDNS, which is a turbulence code, and MILK, those are notorious for high memory bandwidth demand. They have a very, very high increase of from the HBM. For some applications, it's not that important, but on average, I would say HBM is very well worth it. I have another comparison chart here. We have a node or a few nodes with of the Granite Rapids variety with MRDDR, and so that allows us to compare Sapphire Rapids with HBM to these MRDDR nodes, and these are all again single node numbers. And you can see that now that Granite Rapids is probably almost up to 2x faster than Sapphire Rapids. So that will show you that x86 is still going strong when it comes to performance. In this case, I would guess the most natural and easiest explanation is there's a massive increase of core count in the Granite Rapids architecture, and the MRDDR memory provides enough bandwidth for this increased core count. The HBM bandwidth is higher, that there's no doubt about it, but the Sapphire Rapids architecture doesn't provide enough cores to really take advantage of all the bandwidth that HBM can provide. Yeah, and here are the 5 codes: WRF, AMBER, MILK, NAMD, and PSDNS that we have tested. And this is already my last slide here. I also want to do a comparison or show you a comparison with the non-x86 competition. So in this graph, I'm comparing x86 versus Grace. So that's NVIDIA's ARM platform, also single node numbers, and all the nodes were dual socket nodes. If you don't have the numbers in your head, a Grace node with 2 sockets would have 144 cores, 2 sockets, 72 cores each. And we did that for a variety of codes. There are 3 bars for each code, so we are comparing Grace with Cascade Lake, with AMD Milan nodes, and with Sapphire Rapids with HBM, and everything is normalized so that the grace performance is normalized to 1. And if you see the green bars here, if you compare to Sapphire Rapids, you can see if the green bar is shorter than 1, then x86 performs better. And if it is higher than 1, it performs a little bit worse than Grace. You can, from the average, you can kind of see that the Grace performance is somewhere between Ice Lake and Sapphire Rapid nodes, so maybe close to Sapphire Rapids. There are some bars here that are 0.7. There are some bars that go up to 1.3 or 1 to 1.4. But as you can see, we have tested quite a lot of codes here from molecular dynamics or chemistry applications to earth science, material science. Milk is our physics codes, and then some CFD codes like AdCirc and PSDNS. And yeah, that is all I have prepared for you. Again, a very warm welcome to TACC. Of course, it's a little bit a pity that we cannot have this event in person, and we have to make do via Zoom. But I hope you all enjoy the conference, and I'm looking forward to learning a lot about x86 architectures from Intel, and I'm looking forward to the talks. And that's all I have. Thank you very much.
Thanks, Lars. Let's say thanks to Lars from all of us. So we have some time for questions before we move on to our keynote talk. Anyone would like to ask any question? If yes, then they can raise.
I was looking at the chat.
Okay, yeah.
Chat. Yes. So the performance comparison. Oh, I kind of, unfortunately, I stopped the share and let me go back to this one. Yeah. So this. Oh. Sorry, I messed it up a little bit. So in this chart, yes, we are comparing dual socket nodes. So the Grace node has two 72-core sockets, and the CLX is 2 times 28. Milan is, now you have helped me out, 2 times 40, and Sapphire Rapids is 2 times 56. Yes.
There is a second question as well.
Oh yeah, from Steve. Are the comparisons? Yes. Yes, and yes. All is dual socket. Sapphire Rapids is HBM. And yeah, we are using all the cores. Or I hope that answers the question.
And any more questions? If you have any questions, you can raise your hand and or put your questions to the Q&A section of this Zoom platform. Lars, I would like to ask one question about your experience with the new file system on Stampede 3. What kind of...
yeah, we have moved to VAST, and we are quite happy with the new file system. I do not know how many of you have operated a large cluster for a variety of users. The file system is always the most vulnerable part of any cluster that we have operated at TACC, because a single user can create havoc on the file system, and then all the other jobs are impeded. That's completely different than if a user messes up a node and the node kind of leaves the pool and has to be serviced. With VAST, we have had much better experience than with Luster so far. But to be fair, the big test will come when we build Horizon, which will also have a vast file system, and then we are at the scale where we are with Frontera.
Thank you. Any other questions for the Lars here?
Oh yeah, we find slower I/O in Stampede 3 compared to Frontera. Yeah, like in any parallel file system, the performance is proportional to the size of the file system. So Frontera has a much bigger file system, therefore the performance, the aggregate performance is higher than on Stampede 3.
And then we have a question from
Yes.
Miran Radia.
Yes. Yes, of course. On Stampede, let me go to the specific. Oh, where is my slide? There must be this one here. Oops. Yes. So there are 3 partitions on Stampede 3, and for a node hour, you pay 1 SU for the Skylake nodes. On Ice Lake, we charge 1.5, and on Sapphire Rapids, we charge 2. And that represents a little bit the speed up that on average a code would get on these nodes. And we have made adjustments. So we started out with charge rates on Stampede 3 that were 1.66 for Ice Lake and 3 for Sapphire Rapids, and we have lowered those to 1.5 and 2. But I do not expect that the numbers will go lower than that, because that's already a highly discounted rate. I hope that answers Miran's question.